So how can we avoid deadlocks? If we have a priori information about the resource requirements of the processes, we can decide whether an incoming request from a process should be accepted or denied. The a priori information we need is actually how many resources of each resource type a process needs in the future. That information is what we call the maximum number of resources actually of each type of resource. Then the deadlock avoidance algorithm will now look at the current availability of the resources in the system, the incoming request from the process, and see accepting the request from the process may cause a state change in the system which might end up in a deadlock. If so, that request will not be accepted. If not, we can safely accept the request. So at this point, we should define what a safe state is. At any point in time, if you look at a software system where you have the processes and the resources, let's say M processes and K resources, at any point in time, some of these resources are allocated to some specific processes and some are just available. If you create, for example, a vector which defines which resource is assigned to which process, and then also which resources are completely available, that defines the state of the system at that very moment. If you make a new assignment, or if a resource becomes available, that vector will change. So that will be a new state. So the system is actually moving between these states. And the state, if you take a specific state, is said to be safe if from that current state there is a possible sequence of process completions in which all processes can be completed with the resources available at the moment, plus the resources that will become available as these processes complete. Because remember, when a process is completed, when the process ends, all the resources the process holds will be reclaimed by the operating system. Therefore, those resources will become available for the remaining processes. So if the currently available processes, the currently available resources are sufficient to end some process, it could be any process number, but just for the sake of simplicity, let me call that process P1. Okay, so if it's not P1 but P5, I can just do a re-enumeration of the processes and call that one P1, so because you can call the processes as you wish. So once again, if the currently available available resources are sufficient for process P1 to complete, all the resources held by P1 will also become available when it completes. So the currently available resources plus the resources that are currently held by process P1 all will become available for the remaining processes. Now with this enlarged set of resources, if some other process, say P2, can complete, now the set of available resources has even increased more, because now the resources allocated to P2 are also added to the set of available resources. So this way you can find some other process, P3, P4, whatever. Now, if you can complete all of the processes in this way, that sequence of processes P1, P2, P3, P4, whatever. That sequence of completion provides us a path out of this state such that all processes can be safely completed. If this is possible, that state is called a safe state. However, it is sometimes possible that you cannot find such a path. You cannot find a sequence of completion of the processes in which all processes will be complete. Some processes, somewhere in the middle, will just be waiting for each other. And since there are not sufficient resources, those processes cannot complete. If that's the case, then we are in an unsafe state. Okay, so it's important that we are always in a safe state. We don't want to be in unsafe states. So we can say if a system is in safe state, there is no deadlock because we have found a possible order of completion of the processes. Note that there could be more than one such paths, more than one such sequence of process completions in which all processes can complete. We don't care which one is really the reality, in which order the processes will really complete. The important thing is if any one of them takes us to the completion, successful completion of all processes, that's good for us. So if we're in a safe state, we know there is such a sequence, therefore we're sure that there is no deadlock. The processes, none of the processes will be deadlocked. However, if the system is in an unsafe state, which means we couldn't find such a path, in that case, there is the possibility of a deadlock. Not necessarily a deadlock. It is possible that just by chance, some of the processes that were holding a lot of resources just complete and they make many resources available. So suddenly you see an opening and the remaining processes may complete. It is possible, but it's also possible that this doesn't happen and we remain in a deadlock. Therefore, if we are in an unsafe state, we should be afraid of being in a deadlock, or not in a deadlock at the moment, but hitting a deadlock. There is the possibility of hitting a deadlock. So that's something we don't want. So deadlock avoidance can be provided by making sure that we never walk into an unsafe state. The system, when initially started, is always in a safe state. And every time a process wants to use a resource, you're already in a safe state. You check if accepting this request will keep you in a safe state or will it take you to an unsafe state. If it takes you to an unsafe state, don't do it. Don't take the risk. But note that it's not guaranteed that there will be a deadlock. So, in other words, once again, just take any point in time, let's say time t0, in which you have like resource 1 assigned to process 1, resource 2 also assigned to P1, resource 3 assigned to P2, resource 4, resource 5, all of them assigned to P2. P3 is not assigned to any resources, and let's say resource 6 is not assigned to any process. In this case, our state, just at this moment in time, is like, now these are for the resources. We have 6 of them. These are assigned to 1, 1, 2, 2, 2, and this is not assigned to anyone. Now, this is a state, okay? This state is just any point in the set, in the safe state. Okay? You could have other combinations of these of this vector. So every different combination of that vector is a point in this set, which is the set of safe states. As long as you're in one of these safe states, you can go to other safe states. As long as you remain in this set, there is no problem. Okay, you switch from one state to the other by making modifications on this. Like if this one becomes, let's say, available once again, so that means, let me just erase that. There was 2 there, now it has become available. Now it's a different state. So it's a change in the state space. As long as you stay in the safe state set, there is no problem. If one change in this state set will cause you to switch to a state in the unsafe region, although it's not among the set of deadlock states, don't do this. Because if you do that, later that might take you to a deadlock state. But it is not possible to jump from the safe state set directly to the deadlock state. That's not possible. You always have to go through the unsafe states. Therefore, since this will never happen, just avoid using any allowing any switch to unsafe states because it might cause you to go to a deadlock later, in a later stage, not immediately. So the avoidance algorithms can be grouped into, if you have a single instance of every resource type, you can just use the resource allocation graph. That's good enough. However, if you have multiple instances of a resource type, the resource allocation graph will not be sufficient for you. So for that, you have to use what's called the banker's algorithm. So first, let's talk about the resource allocation graph. In the resource allocation graph scheme, remember we had the request edges and the assignment edges. Now we add yet another type of edge. We will call that claim edge, again from a process to a resource, because the process could be claiming that resource type. And we will show that with a dashed line. And the claim edge means that process, PI, might request resource type RJ. Note that I'm saying might request. It's not guaranteed that it will make such a request. But there is the possibility that it might make such a request. Now at this point, you might ask, how do I know whether a process might request a resource or not? Actually, you should have asked this question back in here when I told you about the a priori information. How do I have that a priori information? Well, actually, the compiler can extract that information for you. Because when the compiler is compiling your program, it observes the statements that claim resources. Like you want to write to the screen, so that means you're claiming the monitor resource or some window resource. You want to read from the keyboard, you want to read from a file, write to a file, access a memory location in shared memory, create and write to a pipe. send something over the internet. All these are the resources, and the compiler knows the statements in which you want to make use of the resources, and it also knows which are shared, which are not, which require mutually exclusive access, which allow shared access. So the compiler knows this a priori information, okay, and it can place it in the compiled executable of your program, so that the operating system, when it tries to create the process out of that program, while creating the process, it knows what type of resources and how many of them that program will require. So that the knowledge about that a priori information is something that we can extract, we can know. Okay? So also in here, for the claim edge, I know which resources a process may claim, because from that a priori information, we already have the information. Some of these resources have already been claimed, and the remaining ones are to be used in the claim edge. Once again, when you compile your program, the compiler knows which resources this program needs to access, so that a priori information is already available to the operating system. And as the process is running, it has already acquired some of these resources, and the resources that have not been acquired yet are the ones that could be claimed in the future. So for those, the operating system will keep a claim edge. For example, if you look at this figure, at the moment, process P1 has been assigned resource R1. Remember, if we're using the resource allocation graph, we mean single instance of a resource type. That's why we didn't even show the instances, because there is one in each box. So this only instance of R1 has been assigned to P1, so P2 is waiting for that resource to become available. But from the compiler, the operating system knows that P2 in the future might request R2, and similar is true also for P1. That could also make such a request at the moment, but we have not come to those statements yet. So those requests have not been made, but it is possible that those requests will be made. And that's what we show with the dashed lines. These dashed lines are the claim edges. P2 might claim R2. P1 might also claim R2. Okay, so we have request edges, claim edges, and the assignment edges. Okay, so for example, from P2 to R1, this is a request edge. From P2 to R2, it's a claim edge. And from R1 to P1, that's an assignment edge. So under these circumstances, if you assign R2 to P2 like this, once again, remember P2 had already made a request. P2 could request R2 in the future. If it does so, okay, and that resource gets assigned to P2, now we have a cycle like this. Well, you might say P1 to R1, this one is not assigned yet. This is just a claim edge. You are right, but still it's something that could happen in the future. And if it does so, if P1 in the future, if P1 makes that request while R2 is still assigned to P2, there will be a deadlock. So I'm not in a deadlock state at the moment, but I am in an unsafe state. So I will not do it because this is unsafe. That's the idea. if making this assignment will cause you to go into an unsafe state, don't do it. Okay, that means remain in this graph. This is safe, so this is safe. But if you have this edge assigned, this is unsafe. So the answer is no, don't make this assignment. Okay? So this slide's already explaining that. Now, that was the case for single instance for each resource. What if we have multiple instances of the resources? Then we said resource allocation graph does not help us, so we should work with Banker's algorithm. So here we talk about the Banker's algorithm. In the case of Banker's algorithm, it's very straightforward and simple algorithm actually. Let me just put it this way. Assume that n is the number of processes and let m be the number of resources. So we have n processes, m resources. Then we will talk about 4 matrices. Sorry for the line. 4 matrices. Okay. So first, the available is actually a vector of length m. So that means an element for each resource. If that specific value, like available j, is equal to k, it means k instances of resource type r sub j are available at the moment. There may be more in the system, but some of them have been allocated. K of them are available for assigning to any process that wants it. Max matrix is an n by m matrix that shows at any point in time during the execution of the software system, process n can make a request for at most k instances for resource type r sub j. So for each resource type, this process might at most request this much, for some other type at most this much. But note that this specific value k here includes both the resources that have already been assigned to process I, pi, also the ones pi may later request. So that's the maximum that might happen. Allocation, on the other hand, is a subset of that. In the case of allocation, it shows only the ones that have been allocated to that process for that resource type, R sub j. And the need matrix is actually the difference between the two. The maximum that could be requested minus the ones that are already allocated. So the need array shows how many more that process might request of that specific resource type. Note that we don't need to give the need array. The need array can be easily calculated from the second and the third parameters, max and allocation. So now we can talk about the safety algorithm. By the way, we are not done with the Banker's algorithm. Safety algorithm is a sub-algorithm used by this Banker's algorithm. The safety algorithm checks if we are in a safe state or not. That's where the name comes from. So for the safety algorithm, we are going to make use of the available vector from here, okay? But we are going to modify it to see if we are in a safe state or not. So we don't want to we don't want to change the available matrix, available vector at the moment, because we are not sure whether we will really take that step or not. So we make a copy of the, we make a copy of the available vector in a new vector called work. And also we have another vector for each process. We just mark whether that process could be completed or not. So initially, all processes are marked as false in finish, vector. As we proceed, when we find a way to complete that process, we will make it true. Okay, so we go to step 2 now. Once we have initialized these vectors, we go to step 2 and we search for some process pi, any process, we don't care which one. Find any process pi which could be completed by the currently available resources. Remember, work was initialized to available. So when you if you can satisfy the needs of process I, which is need sub I in part 2b, with the currently available work vector, which is initialized to available, good, that process could be completed. So mark that process as true because we can complete it. And also don't forget to add the resources allocated to that process, which is allocation of I or allocation sub I, into the vector, which is the vector of available resources. That's what we do in step 3. And go back to step 2, repeating this for all processes. So that means among all processes from 0 to n minus 1, among those n processes, doesn't matter in which order, but try to find a process that could complete, good, add its resources, allocated resources, to the set of available resources, and see now if you can complete another one, another process. A process that was previously could not be completed may now be completed because in the previous stage more resources had been added to the work vector. So this way, try to find actually a sequence of processes that could be completed. When you cannot find any other such process pi, go to step 4 and check if all of the processes have been marked as true. If all of them have been marked as true, yes, you have found a sequence in which all processes could be completed. Once again, I could find one sequence of completing processes. You could find another one. Doesn't matter. The important thing is there is a solution that's sufficient for us. If so, this is a safe state. If not, if we cannot find such a sequence, then accepting this request would take us to an unsafe state. Okay? So the resource request algorithm is based on that. In the case of resource request algorithm, which is again a sub-algorithm of the banker's algorithm, you check the request. Now, first of all, the request should not exceed the set of resources that processes allowed to claim. Remember how we created the need I vector. Need I was maximum minus allocated. That means you should not be exceeding that. If somehow your request exceeds that, there's something wrong somewhere. Either the compiler did something wrong or you just modified something, I don't know what. But this is an illegal attempt, okay? So this is just an extra check. Probably you won't fall into this. But if there's no such problem, which is the normal case, the request should not be exceeding need I. As I said, that shows a compiled problem. If so, check if the request could be satisfied with the currently available resources. If it cannot be satisfied with the currently available set of resources, definitely you cannot accept that request. So you should block PI. You should make it wait until those resources become available. But if not, if the request could be satisfied with available, now it's like You want some resources. I have those resources. But I have to make the decision whether I should still accept your request or not. I might reject your request already, although I have those resources, because accepting your request may cause the overall system to go into an unsafe state. And for that, what we do is, let's see what would happen if the request was accepted. So take a copy of the current state, because we might need it. If you don't accept the request, we're going to return to that state. So take a copy of that, and let's act as if that request was accepted. So if it was accepted, I would be subtracting that request vector from the set of available resources, because the resources are, the request is accepted, so the resources should be given to the process, and therefore increment that process's allocation vector by the request vector, and also subtract that request from the need vector, because since they're assigned, you cannot say it will need these in the future. It already got the resources. So just update available allocation and need I, in other words, and see if this new state is safe or not. If it's safe, okay, good. This request is acceptable, and this is your new state, the system's new state. If this takes us to an unsafe state, no, we don't want to take the step. So we don't accept the request now, and we'll just make the process wait. We will not accept its request. So here we have an example, just running that algorithm. So let's assume that we have a software system of 5 resources from P0 to P4, and there are 3 resource types in our system, A, B, and C, with the given number of instances. The system has been running for some time, so at some moment in time, we take a snapshot of the system. Let's call that time T0. Note that T0 is not the beginning. It's just any point in time while these 5 processes are executing. Just at that very moment, this is the picture we see. Very briefly, for example, for P0, it has been allocated only 1 instance of B, no instances of A and C, and if you check the total number of resources it might request any time during the execution of P0, they are 7, 5, and 3 respectively. So one of the resources for B was already given. That means P0 might request 4 more instances of B, but it might also request 7 instances of A and 3 instances of C. By the way, I don't know whether it will really request, for example, 7 instances of A, because while the process is executing, when it comes to an if statement, there's the then and the else parts. If it takes a then part, it might request 2 instances of A. If it takes the else part, it doesn't maybe request A at all. But the compiler does not know at compile time whether it will take the then or the else part. Therefore, the compiler typically looks at the worst case scenario. So it will always put the maximum of each resource type in the maximum array. Okay, so this is the very, very pessimistic design. But still we have to act with that to avoid the deadlocks. So similar is true for all other resources. And of these 10, 5, and 7 instances, at this very moment, we have 3, and 2 instances available. By the way, if you suspect that, you should check, like if you look at A here, 2 of them are assigned to P1, 3 assigned to P2, 2 assigned to P3, so 7 are assigned. In total there was 10, yes, there are 3 remaining. We have 2 resources of B assigned, so 3 are remaining, and 2, 3, 5 C instances are assigned. Out of 7, 2 are remaining. So this is really the available matrix, which is actually the total, from the total, you subtract the allocated. This is your available at this very moment. Now, this, there's no question yet. This is the current state of the system, okay? Now, given this state, you can first of all get the need array. You can construct the need array yourself. We don't need to give it in the question, but you can easily create it yourself by subtracting allocation from maximum in this slide. So that's also obvious. And remember, the available matrix was 332 in the previous slide. Now the question is this system in a safe state? And if you check that, you will see that P1 can complete. Let's go back to the previous slide. Can that? Yeah. Available is 332. Okay. So if you look at the max, and from here, let me, besides max array, in between, let me write need. Let me just easily write that this is 7, 4, and 3. I'm just subtracting allocation from max. This is 1, 2, 2. This would be 6, 0, 0. And here we have 0, 1, 1. And this is 4, 3, 1. I've just subtracted allocation from maximum and created the need array myself. And currently there are 332 available. So which one of these processes could complete with the available resources? Note that we could start with P1 because 1, 2, 2 can be satisfied by 3, 3, 2. Fine, because each value is less than that, one by one. Actually, I could have done it as 0, 1, 1. As you can see in the next slide, the answer starts with P1. So there's already that solution. So let me try to find another solution, the alternative solution. That one is correct. This is an alternative solution. Let me start with P3. Now, when P3 completes, so it is possible that it will complete. And when it completes, all the resources that have been assigned to P3 will become available. So this 322 will become, let me add 211 on top of 322. So it will become 5, 4, and 3. This is the new available vector. So after P3 completes, with 5, 4, 3, which processes can be completed? P1 can be completed. That's trivial. Can I complete P4? Yes, I can also complete P4. Now, see, I'm finding an alternative solution. Even in the alternative solution, I have two alternatives. So I could have completed P1 or P4. I will pick, in this case, P4. So this is also completed. So all the resources allocated to P4 become available. So this will become now 5, 4, and 5. Those two resources for C are now added to available. Now, which process can complete? By the way, let me also write on the side. I first completed P3, then P4. So this is my sequence. P3, P4, then, sorry. Let's see then what. With 5, 4, 5, I can complete now. I cannot complete P2. I cannot complete P0. There's one option only, P1. So when P1 is completed, I should add 2, 0, 0 here. So this will become 7, 4, 5. With 7, 4, 5, I can complete P0 or P2, whichever one you want. Again, you have alternatives to alternatives. So let me say I complete P0. So when P0 is completed, I will have 7, 5, 5 available. And then P2, can it be completed? Yes, it's 600. Since it could be completed in the previous stage, it can also be completed now. So when that is completed, 302 will become available. So that means 10, 5, 7, and P6. So this is the sequence I have found now. In the next slide, you have another alternative solution. As we have seen during the calculations, there were even more alternatives to alternatives. So this is possible. And also note that I'm left with 10, 5, and 7 resources, which is the original preservation of the resources, of course. We are not eating up the resources. So this shows an example of using the banker's algorithm. What if, now we have shown that we're currently in a safe state. Now what if P1 makes a request of 102? Okay, first of all, does P1 have the right to request 102? That's the first thing you should check. Okay. Since you check if 102 could be satisfied by 332, then it is acceptable. And if you do that, is there a safe sequence out? And we can find, I will not go over that, but if you want, you can just try it as we did before. It is possible to find at least one sequence that takes us to the completion of all processes. Therefore, it's a safe step to take. So yes, we will do it. Just try as an exercise whether you can request, whether P4 can request 330 or P0 can request 020. Just do it as an exercise.